All right. How's everyone doing today? All right. So, thanks for putting up with not having lab for the last couple of weeks. Hopefully that wasn't too bad. So, to make up for that, we're going to be doing Lab 9 today. And then if you want to stick around, I'm going to be going over Lab 10 as well because of the way the rest of the class is kind of scheduled. There's no more weeks that we can have both labs meeting due to like Thanksgiving, and then we have the last week of class before finals. But Lab 10, we're going to just treat it as bonus points. So if you do that, do a report, turn it in, I'll grade it, and add those as bonus points to your grades. Yes. 10, I guess. Yeah.
That's one lab, right?
Sorry.
That's one lab. 10 points.
Yeah. Yeah. So we're going to be doing Lab 9, that's normal. So do that. Lab 10, that's optional, but if you do it, get bonus points for that. Should have been in the email I sent last week or the week before. But today we're going to be going over Lab 9 here first. So we've got two files here. Let's open up the PDF first. Okay, so what I'm going to be teaching you in this first lab here is we're going to be showing you how to import geometry into SAP2000 and then run a model based off of that. So a lot of the time, I'm sure you can imagine, structures are more complicated than what you can just generate using one of the templates. The columns aren't all in nice, perfect grids that are evenly spaced, and the floors are all sorts of different heights, and there can be weird geometry in a building. So what we can do then is we can go and import some geometry that we make in another program. Usually I like to go and draw my kind of more complicated structures in something like AutoCAD or another program like that, and then we can save it as like a DXF and then import that into SAP to go and do the analysis on. So I've gone and put together a model and saved it as a DXF, which is a drawing exchange file, which is AutoCAD's file type that works with other programs too. And SAP is one of those. So I went and drew a 3-story building in there. And what we're going to do is we're going to import that geometry and do the analysis. So the model, it's going to be 5 bays in the X direction, spaced at 20 feet, a single 48-foot bay in the Y direction. There's 3 stories. Each of those are 12 feet high. We're going to have chevron braces that are located in each of the XZ frames. The girders are attached to columns with moment connections. And then all beams and braces are connected with shear connectors. So this is a bit of a complicated model if you go and look at the figures that are attached. So here's in the YZ elevation. So this is that single 48-foot bay. In the XZ elevation, these are the 5 20-foot bays. And if we look at the floor plan, that's how we want to lay out the spacing. So these girders here, the W24 by 131s, those are attached to the columns with moment connections. And then everything else is a shear connection. So I'll show you how we go and model those. So once we do that, we're going to import all that geometry with or from the file I've attached here, so you don't have to go and figure out how to draw all that. And then we're going to use area loads that are applied to each floor, as well as the windward face of the building. And we're going to consider the self-weight of the structure to be present. So we're going to use pounds, inches, and Fahrenheit for this one. Everything's going to be steel. We're going to be using W14 by 34 beams, W24 by 131 girders, W18 by 97 columns, and HSS 6 by 6 by 1/2 braces. We'll be using the same 2 load combinations, and for the area loads, these are the dead, live, and wind loads. Any questions on this so far? So this is a bit more this is a bit of a more realistic structure than some of the ones we've been doing so far. So this can help show you how we would want to utilize some of the tools in SAP to make this process a little more efficient. Okay, so first things first, let's go back to Blackboard here. We've got the second one, the second file here, this DXF. So let's download that. So that includes all the geometry for our model. And then when we've downloaded that, we can go and open up SAP2000 and start ourselves a model. So when we have SAP open, we'll go and make ourselves a new model. It'll take itself a second. Okay, now when we open this up, we have a couple things we need to do. So first is we need to put in our units. So that's going to be pounds, inches, and Fahrenheit. So let's select those. And second, we want to select our template. Now, because we're going to be importing all of our geometry, we're going to use the blank template. So that has just nothing in there by default. So we'll click on blank, and it'll go and create ourselves our workspace with our coordinate system and nothing else. Give that a second. And then let's go and close that, maximize that so we can see what's going on. Everyone with me so far, or does anyone need another second or two to catch up? Okay, so what we're going to do then is we're going to go to File, and then we're going to go to Import. And then in that list of different file types it can import from, SAP can interface with a whole lot of different programs. We're going to go down about 60% of the way to AutoCAD DXF file. So we'll click on that, and then we'll want to navigate to where we went and downloaded that DXF file. So it's probably going to be in our downloads here. So for this one, it's called Lab 9 Example Geometry. So let's go and click on that. Then we can open that up. Okay, and then in the file here, the units that the file's in are going to be in pounds and inches and Fahrenheit. So you want to make sure that kind of the units you went and drew your model in correspond to the units that you're going to be using in SAP. So you're not importing something that's way too big or something that's going to be way too small for what you want it to be. And the reason I went and chose pounds and inches and Fahrenheit for the units we're working in SAP here is because I went and drew my model using the engineering units in AutoCAD, which base to inches there. And then the global up direction in our model is going to be positive Z. And that's the global up direction in the DXF as well. So both of these options are okay. So click on that. And then what we want to do is we get this DXF import menu here. Now, when we're importing models into SAP2000, there's a whole lot of different types of elements we can import, including joints, frames, nonlinear links, shells, and solids. What we're doing today is importing frames. So I have 4 layers in the DXF file, and I named them after the section that you should be assigning to them. And those are the HSS 6x6, the W14, 18, and 24. So what we want to do is we want to check all 4 of those in frames. So SAP will say, okay, I'm going to import everything in these layers in the model as frame elements. You could go and check them in any of these other ones, and it'll get all confused because it won't have the right data to import them as like a shell or a solid. But click it as frames, it'll import them all as frame elements. And the very nice part about version 22 is for each of the layers, it'll import it as a group as well, which makes handling imports way easier. Back in version 15, which I used to teach before I got him to get version 22, it didn't go and group them. So you'd have to import them one at a time, then make it a group, then import the next one, then make that a group, and so on. And that certainly helps a lot for assigning the correct properties to each group of frame elements you import. So that makes sense to everyone? Okay, so basically check everything under frames here, then we say okay. And we should have our geometry for our building imported now. So we should see that it's going to be 3 stories tall. We've got one bay that's kind of wide here, and that's 576 inches wide, which is the same as 48 feet. Then from the origin to all the way right here, it's 1,200 inches, which is 100 feet, which is 5 bays each at 20 feet. They're each 144 inches tall, so 12 feet. So looks good. So this is all the geometry that we've imported from the DXF file. So a lot faster than going and trying to draw it all by hand in SAP, don't you think? Good. Okay, any questions so far? Everyone's geometry looking like this? Good, it should. Okay, so we have a couple things we need to do now. So if I, for instance, click on this member and right click it. Oh, wow. Okay, no, that didn't do that quite right. So if you look, it has a section property of 18 by 35. That's the default property for frames when you import things into AutoCAD or into SAP, or when you like draw frame elements, that's the default frame element size. So what we need to do is we need to go and import all of our cross-sectional import all of our cross sections now, and then assign it to all of those, as well as add our boundary conditions as well. And then we'll need to make areas for our floors and the windward face of our building too. So first things first, let's go and import our cross sections. So we'll go to define, then section properties, then frame sections. You see we've got 18 by 35 here. That does not correspond to any of these here. That's just the default frame section that SAP will give something if it doesn't have a cross-sectional property. So we want to import these 4 properties here. So import a new property. First 3 are going to be wide flanges, so click on that. Scroll down to AASC15. Open that. And then we'll scroll down to W14 by 34. We'll click on that. Then we'll go to W24 by 131. We'll press Control to select that one as well. And then we'll scroll back up to W18 by 97. And we'll click on that one as well. So we'll have W14 by 34, W18 by 97, and W24 by 131 all selected. We'll press OK, and then OK. And then we have all 3 of those in there. And then we want to import the HSS 6 by 6 by a half as well. So we'll go and import new property again. We'll click on the square tube. We've already selected the AISC15 database, so it's just pulling straight from that now. So we'll scroll down to HSS 6 by 6 by 1/2. So 6 by 6 by 0.500. And then we'll click OK on that. And then OK on that. And then we've imported everything. So we can say OK to that. Okay. Everyone good with that? All right, so now we want to assign our frames to the correct members. So the way we'll do that first is we'll go to Select, and then Select, and then groups, or we can also use Control G to select a group. And you see we have 4 groups in here. When we imported those 4 layers from our DXF, it went and automatically generated these 4 groups that correspond to all the elements it imported from those layers. So this is really helpful for us to go and, assign the correct cross-sectional properties to each of those elements without kind of having to hunt through the model for where each of them should be. So let's start with our columns. So that'll be 18 by 97 here. We'll say select that. And if we look at our model, it's gone and selected all the columns in the model. And then we can go to assign. Well, we'll close that. And because we have our column selected, we can go to assign, and then frame, and then frame sections. We'll pick 18 by 97, and then say OK. Yes.
So, are the columns like selected automatically from the model because you define them in AutoCAD, or?
So in AutoCAD, when I was drawing this geometry, I went and put each of the, I went and drew a line for each element in the model there, and I assigned them to a layer, each of them to a layer based off of what cross-section I knew it would be for this. So for all the columns, I said that would be part of W18 by 97 layer, basically. And because we imported them, all 4 layers into here, we have 4 groups. And if we select the W18 by 97 group, that winds up being all the columns, because those are the numbers I went and assigned to that layer in AutoCAD, basically. So it's not like trying to suss out what each of the numbers should be just from the geometry here. It's because that's how I modeled it in the DXF. Yeah, you can call the layer whatever you want. My convention I like to use is I'll go and give each of the layers in my model the cross-sectional designation that I want to assign it in my analysis model. It helps me keep things straight, but you're certainly welcome to use whatever convention you want. Okay, so we see we've assigned our W18 by 97s to our columns here, but everything else is still a W18 by 35. So let's go and repeat this 3 more times for the other 3 cross-sectional properties. So this time I'm going to press Control G, bring up the Select by Groups menu again. Let's assign our girders. So that's going to be the W24 by 131s. So I'll select that, close this menu here, and we see that the girders are these long 48-foot members between the columns. So I'm going to assign frame sections, click on W24 by 131, and then press OK. 2 more to go now, so we'll press Control G again. We're going to do all of the beam elements between the girders now. So we'll select W14 by 34, select all those, close this, and we see this is all of our beam elements selected now. And to assign the correct cross-sectional property to all of those, we go to Assign, Frame Sections. Then we'll click on W14 by 34, press OK. And then the last are going to be these chevron braces. We're going to, again, press Control G. Then we're going to click on HSS 6 by 6 by half, select that, close that. You see we've got our 12 braces selected there. And then we're going to go to Assign, Frame Sections. And then we're going to select HSS 6 by 6 by half, then press OK. So if we zoom in on our model, all of the cross sections should be correctly assigned now. Any questions with that? Cool. Okay, so that's all of the cross-sectional properties. Next thing we want to do is apply boundary conditions to our model. So to do that, all of these are just going to be treated as fixed. So let me just select the 12 base points here, and then we will go and assign joint restraints. Click on the fixed fast restraint here, so everything's checked. Then we press OK, and we see we've got our fixed conditions at the base there now. Okay, any questions on that? Okay, so we are, yes.
I have a question on this protocol. Over to show me the shape. This kind of
Showing you a deformed shape. Have you run your analysis yet?
it
That's-
did prompt me a little while ago to save my file, even though I didn't tell it to process.
Oh, that's weird. Let's
Yeah.
see.
It's like the map selected that means your model is five. So basically, every change you make, it goes and runs their analysis and that they don't go a bit line. So as long as it's great.
Okay. Yes. Oh, no. Okay. I thought you were raising your hand. Okay. So before we're done with the geometry, we have one more thing we need to do to handle kind of the geometric modeling of all of our frame elements. If you remember, it said basically everything is connected with shear connections and then some of them are connected with moment connections. So this is based off of how we generally model structural connections when we're doing structural engineering. We can go and make everything so that they're all rigid connections and transfer moment in all axes. Those connections are more complicated and more expensive because you need more steel and more plates and more labor to assemble them. So generally, when we're designing buildings, we try and eliminate as many of those moment connections as we can. So in the design of the building that I've gone and put together for the lab today, the kind of structural system we have is in the YZ direction, we have a moment frame. So these girders are connected with moment connections to these columns. However, in the XZ elevation here, we have a braced frame. So we have these diagonal braces here. So we don't need moment connections in this direction to maintain stability in our frame because we have these diagonal elements here doing that for us. And in the plan view here, we don't need moment connections between all of these beams and our girders as well, because having basically simply supported beams between all of the girders here also works. We get a little bit more deflection, but it's generally well within acceptable realms when we're designing here. Does that make sense what we're doing? So basically, we're trying to simplify all of our connections as much as possible to increase the economy of our building, basically. So when you're designing actual structures, this is something you need to take into account. Most of the connections aren't moments, and usually in a plan, they'll go and designate, in a structural plan, they'll go and designate moment connections with these little solid black triangles here. So what we're going to do is, to model that, is basically do moment releases, just like we've done with trusses. We're going to release our moments for all of our W14 by 34 members here, and all of the brace members here, the HSS 6x6 by half members there. We don't want to release any of the columns because those need to remain continuous, and we don't want to release any of the girders because those are connected with moment connections to the columns here, but we want to release all of the beams here and all of the braces there. So in our model here, we can again use our group select. So we'll press Control G. Let's go and select W14 by 34, as well as our HSS 6 by 6.5. So we've got all of those selected. We should have 117 frames in total between the braces and the beams. And what we'll do to release those moments is we go to assign, then we go to frame, and then we go to releases / partial fixity. So fourth one down. And just like we did when we were modeling trusses, we go and release the minor and major moments at both ends of the beam. Minor and major. So major is kind of in the direction of the strong axis of the beam, and minor is in the direction of the weak axis of the beam. So usually we go and put the strong axis up to handle the gravity loads, and the weak axis is kind of lateral to it.
Right.
So it's handling it kind of in plane for strong axis and out of plane for the minor axis.
So it's like the minor is like X to Y.
Exactly, yes. Well, each of the elements has its own local axis as well, but exactly. Yeah, so we check those bottom four, and then 0 is okay in all of those. So we say okay. And we see in our model here, we've got a lot of green dots. Basically, each of the moment frames in between are still all attached together, but we have a lot of separate beams connecting them together and bracing the frame in this direction as well. Yes. Yes, exactly. So in reality, it's not literally a big pin. You'll have a couple bolts there, but it's ductile enough to act pretty close to a pin. If you want it to act fully fixed, you need a lot more bolts, and the connection needs to be bigger and, you know, connect to all the elements. So like the top flange and the bottom flange and the web, rather than just a couple bolts in the web. So it's much faster to go and connect elements like this, and modeling it like this is more conservative than pretending it's still going to be a fully fixed connection. So that makes sense? Okay. So that's good. I'm going to show undeformed shape here to get rid of all of the releases. And I know I said that was the last one, but I remembered one more. So I'm going to show you how to look at kind of the extruded view for each of our elements here, just to make sure they're all in the correct orientation. So we can press the check mark box there, then go to general options. And then in view type here, we can click extrude. So use the check mark box for view options up here. It's on the second tab here, general options. Then we use extrude here. So we'll say okay to that. And this goes and extrudes out the elements so you can kind of see how they're oriented in 3D. So let's say we zoom in here. We've got our girders up and down, so that's good. We've got our beams going this way, so that's good. Our columns are going up and down, so that's good. However, if we look at the orientation of the column, the strong axis is going in the direction of our braced frame. Whereas in our drawing here, we want our beams to have the strong axis in the direction of the moment frame. Notice that? So what we want to do is we want to basically turn all of our columns 90 degrees so that their strong axis is acting in the direction of our moment frame. Whereas right now, as they are in here by default, they're not. So what we're going to do is we're going to select the column group here, the W18 by 97. And then what we're going to do is we're going to go to assign, frame, yep. And then the fifth one down here, local axes. We're going to put in here 90 degrees. So that's going to turn the local axes of here, of these columns by 90 degrees about the longitudinal axis of the member. There's other ways we can mess around with rotating them as well, but this is the most common way to do it. So we just put in 90 here, press OK, and we see that all the columns have now turned 90 degrees and their strong axis is in line with the moment frames. which is what we want to model. Does that make sense to everyone? Now, we need to make sure we do this, otherwise we're going to be considering the strong axis of the column in the wrong direction, where it's not really being used too much. And we're going to get much worse performance in the moment direction. So we want to utilize the strength of our cross-section in the systems that we can for it. Okay, so any questions on this so far? Okay, so now let's start setting up our loads. I'm going to just switch this back to the standard view. So it's just lines for now. And then I'm going to turn off the local axes by just clicking on the show undeformed shape. Okay, so let's go to define, then load patterns. We've got our dead load with a self-weight multiplier of 1, so that's okay. We need to add ourselves a live load and a wind load. So let's do that. In the wind load, make sure we set that to none. And then we'll add that load pattern. And we'll say okay. And then for the load combinations, we'll add those. So we'll add a new combo. For combination 1 here, we want it to be 1.2 times the dead load. For the live load here, we want that to be 1.6. And for the wind load, we want that to be 0.5. So that's our combo 1 we've been doing. 1.2 dead, 1.6 live, 0.5 wind. So we press OK to that. Then I'll add the second combination. So that's going to be 0.9 times the dead load. And then that's going to be 1.0 times the wind load. And then we'll say OK to that. And then OK to our load combinations. And then before we can apply them, we need to do the same thing we did, I guess it was probably 3 or 4 weeks ago now, where we go and make that kind of area that we can apply those surface forces to. So to do that, we go to define, section properties, area sections. We're going to, it's already got asec1 here. So if you've got that, you can just say modify / show section. If not, you can just say add new section. We'll call that, basically, we want to make it 0 width. So we say it's going to have 0 membrane width and 0 bending width, or 0 thicknesses here. And then this shouldn't matter. So as long as we set both of these to 0, we can say OK. Then we can say OK to that. And now what we need to do is we need to go and draw on basically our floor plates using these sections that have no properties because it's got 0 thickness. It's not going to contribute any stiffness to our model here. So what we're going to do is we're going to go to draw poly area on the left here. Select the section we did. So I called mine null. You can name yours whatever you want. Click the 4 corners of a floor, hit enter, and you see we've got a red outline on the floor. So we'll do that for all 3 floors. And then finally, we'll do that for the windward face of the building. So usually where we go and put those point loads for the winds, we're going to use an area load today. So we're going to draw one of these areas along this face of the building here, press enter, and we've got it there. So, winds are usually applied as a pressure. So let's model them as a pressure today. Any questions on that? Okay. So let's see what loads we want to apply today. We want to apply a 30 PSF and a 100 PSF dead load and live load to each of the 3 floors. So let's select the 3 areas for going over our floors here. Then we'll go to assign, area loads, and then uniform to frame. We'll start with our dead load. Global gravity is okay. We'll change it to 2-way. And then our load will be not in PSI. Let's change that to pounds per square foot. We'll put in 30 PSF there, then say okay. So we've got 30 PSF going downwards on each of these floors. We'll select all of them again, so we can do Control J to select the thing we just had selected. Then we'll go to assign, area loads, uniform to frame. Same thing we just did. Same settings, except we choose our live load, and it'll be 100 PSF now. We say okay. And that's our live load. Dead load's still there. This is just showing the live load. And we want to add a 30 PSF wind load to our windward face here. So we'll select that. Then we'll go to assign, area load, uniform to frame. We'll select wind, coordinate system global is okay. Load direction, we want to change that from gravity to X. 2-way is okay. And then our load should be 30 PSF. And then we say okay. Any questions on that? Yeah, they're all 2-way. Yes.
Can you show the how to set up the wind loading?
Yeah, so we'll select our windward kind of shell element we put on our model. Then we go to assign, then we go to area loads, and then we go to uniform to frame. And then we want to put in the wind for the load pattern, global coordinate system, it stays that way. And then we want to be loading in the X direction because it's perpendicular to the face, and that's going to be in our X direction here. So we say that's X. We can keep that as a 2-way load distribution, so it'll go to the columns as well as the floors. And then it's 30 PSF for this one. Then we say okay. Everyone else okay with this? Any questions? Okay, so once we're happy with that, we've got all of our geometry modeled. We've got all of our loads put in there. So then let's run our analysis. So we can say run analysis. Let's not run the modal case, but we need to make sure we run dead, live, and wind. We'll say run now. It'll say save it. So we'll do that. We'll make ourselves a new folder for it. Let's save that. It'll run. It'll take a minute. There's a couple, there's a good number of elements in here. And you see here, it's showing the dead load, and it's kind of exaggerated at the moment. But yeah, this is what happens in these types of in these types of systems. We have each of the beams kind of sagging between each of these perpendicular braced frames that we have set up here, or moment frames, sorry. And then, yeah, okay. Everyone get their model to run all right? You guys all right back there? Okay, cool. So let's look at the deliverables we want for this one. We've got 4 of them. We want the reactions for each support with values and arrows for the XZ frame at Y = 0 for load combination 1. So our XZ view is going to be this kind of long side elevation view at Y = 0 for load combination 1. So let's go back to SAP for that. Let's go view, set 2D view, XZ plane at Y = 0. There is all right. And then we say okay. And then what we're going to do is we're going to go to display, show forces, stresses, joints, select combination 1, and then press OK. So those are all of our reactions for those fixed supports in this plane here. And you see we've got our reactions as forces as well as moments here. So the double-headed arrows are moments about the axes they're rotating using the right-hand kind of curl rule convention. So like this one is pointed up, so right hand, it's going to be curling this way. What's happening?
We didn't get the same value.
Uh-oh. Like
1 minus 10 to the 8th.
10 to the 8th. Are you in pounds and feet?
Yeah.
Interesting.
Oh, no, wait,
It shouldn't be 10 to the 8th, but
Can you?
I
can you change
switched
your-
to pounds.
I think that
Make a
the-
difference.
I
I
didn't
think
count
the lab was probably-
inches are getting the same values.
Yeah, I'm switching. Are you?
Oh, I'm in pounds.
32,000 on the side as well?
No,
So this is pounds and
No,
inches
it's
for me.
126.
Interesting. You checked and your model was the correct size when I was showing what the sizes should be, right? Okay. Interesting. Did you make sure you were importing your, did you switch it to pounds and feet when you were? Okay, so I'm guessing when you put in your area loads, you were putting those in as PSI instead of PSF. So your loads are 144 times too big. So that would probably do it.
Yeah.
How do you remove all the loads of the-
Well,
It's just easier to overwrite.
overwrite them. You could also just delete the plate element. That'll get rid of all those loads at the same time too. Either's about as fast. Okay, so those are the reactions here. Let's keep going. So the deformed shape here for the XZ frame at y equals 0 for load combination 2. So we're gonna keep the same view here. We're gonna go to the deformed shape, select combination 2. I'll turn on wire shadow for this, press OK. And it hasn't deformed all that much. So let me go into the deformed shape here. If we're not happy with how much it's exaggerated our deformed shape or not, see we can go and up the amount of deformation. So let's say I want it to be exaggerated 500 times. I can switch the scaling here from automatic to user defined and put in a scale factor I want. So let's say I want it to be 500 times exaggerated. So I can say okay there. And now we can get a bit more of a sense of how much it's exaggerating. And why it gave us a really small exaggeration here is because it's moving laterally like this, much less than those girders are deflecting downwards out of view here. So it's basing its automatic scaling on their deformation because it's the most deformed part of the system. Make sense to everyone? Okay, so that's deformed shape. You guys don't have to mess with the amount of deformation if you don't want to. It's just for your knowledge. If you do want to exaggerate something more or less in your model results, I would never exaggerate anything less than 1 times what it's actually going to exaggerate, because then you're kind of covering up how much it's going to be deflecting. But for a scale factor, it's good to, scale it more if you're trying to see exactly how much it's deflecting. Or at the mode.
Defined and
Yeah, user defined. I went and set this one to 500 instead of 100. That's what I'm getting here. Okay. So the next one, we want the shear diagram for the XZ frame at y equals 0 for load combination 2. So that's just our shear diagram. So we'll do shear 2, 2 here for load combination 2. Show values, then say okay. So those are all of our shear diagrams here. We can break those out with the object shrink toggle. Let's see.
Change your view, is that the same view?
This is the same view, the XZ plane at y equals 0. So for all of these deliverables here, I've asked for them all in the same plane. Okay, yeah, you can't really scale those, so this is fine. Then I asked for any, no, I didn't ask for any maximums here. Okay, and then finally the moment diagram, same thing, just moment 3, 3 instead. So you see on each of our beams here, that's just a simply supported kind of parabolic moment diagram there. Nothing fancy going on at either end. And then we've got a bit of moment going on in each of our frames here.
Pretty sure.
Oh, weird.
Let's see what you got. It's a pretty sure. Yeah. The shear is right.
Oh,
You hooked on two of these.
Two waves.
Everyone else getting these okay results? Okay. Yeah, you gotta be. I'm gonna do that. Oh. That's language. Okay, so let's, if you guys want to stick around, I'll stick around to go over lab 10. It's a little shorter than this. Let's take a break while I stop the recording, get that processed, and get set up for the next one.
oh, you never stay out left. Whatever, yeah, fast one.
What's that?
You don't want to.
I'm gonna split them apart so I can post them in as their own